So today is practice day. Ask questions. And even to help some of the everyone has different backgrounds, some in the life sciences, some in the physical sciences. So maybe people have questions, but they're a little shy about asking. So if you understand a good time for a question is now, you see I didn't explain something just like you want, and you even know the answer, you can still ask the question so other people can benefit, okay? This slide is out of order, but it's one of the most important ones I'm going to show you today. And in fact, I think my job today and tomorrow is to get some concepts across, because as the days go on, you're going to have lectures from other people about different aspects of synchrotrons or free electron lasers or coherent imaging or something. So you're going to hear about these things again. I would just like to get the concepts over. And so if the concepts are not clear, please ask questions. And as long as I have this one up here, let me just start with it, and then I'll go back and start all over again. But if you had an electron oscillating in and out of the board, it would radiate electromagnetic waves. Whenever a charge is accelerated, it radiates. So if an electron is oscillating in and out of the board, it's radiating spherical waves out, okay, at some wavelength. And if this thing was moving and you were over here, there would be some Doppler shift. Shorter wavelengths would be observed, right? So this one, we're all used to Doppler shifts, right? If it's moving away from you, the wavelength seems a little longer. In the relativistic case, where the electron is moving extremely fast, approaching the speed of light, this Doppler shortening is going to be a really major effect. And when you ask, why are we seeing X-rays out of these machines, like ESRF or Electra, where the electrons are going around the ring at very high relativistic velocities, where this Lorentz contraction factor, you know, which you've, I think even from the life sciences, you've seen this probably in high school. Gamma is this contraction. You know, the meter stick seems shorter when the rocket ship is going faster. It's 1 over the square root of 1 minus v squared over c squared. So when v gets very close to c, this Lorentz contraction factor gets very big. And we're going to see here that the Lorentz contraction factor, for instance, at ESRF, it's something like 12,000. So this diagram, what happened? So this diagram doesn't quite capture it. Here the electron is oscillating in and out of the board, just like here. So it's radiating spherical waves which are moving away. The peaks are moving away at the speed of light. So here they're moving away at the speed of light, but the electron is almost going at the speed of light. So if you're observing from this direction, there's a great contraction here. It's probably one of the best things I'll show you here today is this diagram, and it becomes extremely short. And this is for a modest value of gamma. When you get up to gamma equals 12,000, this winds up, even though this oscillation in the laboratory frame might have seemed a much, much lower frequency, much longer wavelength, here you're going to get X-rays out of it. So does someone have a question or comment now? We're going to come back to it in a moment. So that's, let me see. So let me go back to the beginning of the talk. So this is the electromagnetic spectrum, right? Here's visible light, red to blue, as we're used to. The wavelengths here, for instance, green is 500 and something nanometers, okay? We're going to be out here with wavelengths of nanometers or angstroms or something like that. So this is the region of X-rays. We generally break them up into soft X-rays, energies around a kilovolt or 500 eV or something like that. This is where the iron L edges are for people who are interested in magnetics and stuff like that. Hard X-rays would be your medical X-rays would be out here, protein crystallography in here someplace. This is where the copper K alpha radiation is, wavelength-wise. So there's photon energies along here. Here you'd have a few electron volts, green light about 2 eV, okay? And on the top, just by F lambda equals C, and then replacing F by omega and K, etc. These are the wavelengths that go with these photon energies, okay? So we're going to talk at this workshop school about mostly in this region, a little bit in this region. For instance, here's the silicon L edge. So it's for this, it's also an important area for some people. The L edge is around 99 eV or something like that. I will give you an example tomorrow which is just below the L edge. So if you're below the L edge, there's not so much absorption. If you're above any of these edges, there'll be more absorption. Okay? See if I get used to this. Oh, whoop. So I should have said the obvious. With the tunable radiation that we can get from a synchrotron or a free electron laser, as we'll learn, one, we have elemental and chemical sensitivity. If we can choose our photon energy to be near some absorption edge, so probably our PhD thesis involves atoms of a certain kind, okay? So let's say, choose something different, near the carbon edge. Okay? You want to tune your photon energy. For instance, in an image, you'd like to see mainly the contribution of carbon more than the other elements that are there. So you'll choose your photon energy to be on one side or the other. If you choose your photon energy to be just above the carbon K edge, you have a strong effect, and your image or your spectroscopy or something will be more dominated by that. If you stay on the low side, there's less absorption. I'll explain why in a moment. And so by tuning your photon energy to the edges, the absorption edges of the atoms of interest, that's usually where the thesis starts. So that'll put you into the soft or the hard X-ray region. Okay? Oh, I keep with the hard X-rays, you can penetrate things which are opaque by visible light, okay? In the hard X-ray region. This soft X-ray region, absorption is more important, okay? And because the wavelengths get smaller here, you can see smaller features. So you'll do, some of you are probably involved in doing imaging at the nanoscale, so nanoscale imaging. If you're working with a free electron laser, you may be combining nanoscale imaging with femtosecond time dynamics, or maybe even so femtoseconds. And you can write smaller patterns. So you could reverse your optics and you could write a small pattern. That's what's going to come up over here. The latest computer chips, which are now being made by Samsung and Apple, not by those people, used by, in smartphones by Samsung and Apple, use computer chips which are just started being made a few months ago with a completely new technique which works on a wavelength of 13.5 nanometers just on the low side of silicon, where the silicon is not absorbing. And these are called extreme ultraviolet computer chips. You could search it, you'll find it. So you could reverse the optics. This is a convenient conversion formula. It's telling you that the product of the photon energy and the wavelength is equal to this product. So if I told you you had 1,000 eV, you'd put 1,000 eV here. The EVs cancel out. The 1,000 divides over. And you'd move the decimal point and say that lambda is 1.2 nanometers. So that's how you use the formula. So as you go through the lectures over the coming weeks, it's convenient. And tomorrow we'll talk more about the refractive index for X-rays. So you know, like for instance, visible light going through a window, the refractive index, you probably know, is something like 1.5 or something like that. It's 1 plus something. But for X-rays, it's 1 minus something. It's minus a small number. We call it a decrement. It's so small. But it makes a big difference in optics that we can use, the techniques we can use. And you'll hear about that tomorrow. Okay? Just to get everybody on the same page. If you have some atom with a charge Z on the nucleus, you have a photon coming in of this energy, and you knock out an electron from what's called the K shell, out goes an electron, there's some binding energy to get this electron out into the continuum. Okay, that's called the binding energy. And if this photon energy is less than that, it won't go out. Okay, it has to have enough energy to kick it out, and then the electron is called a photoelectron, and whatever excess energy there is, it becomes the kinetic energy of the electron. So that's what we call the photoelectron. Of course, the atom is then unstable. It's not in its lowest state, so it'll relax, and another electron will drop down and could throw out a photon, could throw out another electron. That's called Auger. What are the, by the way, this is the principal quantum number n equals 1, n equals 2, n equals 3, but in the X-ray world we call them K, L, and M. And here is shown a few of the binding energies. How much energy does it take, for instance, copper is a common one, Z equals 29, to take an electron out of the n equals 1 shell, the K shell, okay, K absorption edge it's called, takes 8.3 kilovolts. Okay? So that's how much energy is required to get an electron, if this is 29, to get it out. Okay? To get one out from the L shell, of course, there's a lot less energy. It's not as close, so the binding is not as strong, and there's a little shielding by the inner electrons. So for copper, the binding energy is 930 something. Okay? So you can see where if you choose your photon energy, you can tune around one of these edges. Okay? This is just more complete. This, I meant to say, this is a very simple diagram, okay, showing the K, L, M shells with the principal quantum numbers that matches this. So you could see if it had a photon energy of this much, and you took an electron from here to the continuum, this would be the excess kinetic energy. Okay? It's a kind of simple thing. It's just showing the principal quantum number, and we don't need to go through this. But of course, we have angular momentum, and except for the K shell, all the others have splittings of energy. Okay. And this is, it's not so much that I wanted to give you all this information, but I wanted to tell you about this website. If you work in the X-ray energy region, you'll get to use this. It's very convenient. It gets more than 1 million hits a year. You can look up all of these absorption edges. You can look up refractive index or atomic scattering factors. Okay, so that's the reason for this slide. And this one is just to say that with synchrotrons and tunable photon energy, you can basically pick any element you want and go search it out through spectroscopy or imaging or scattering. Okay. And also for synchrotron radiation, you can do all kinds of science. So probably with the people in this room, you're probably all doing something of this nature and even more. Whoops. What am I doing to myself? Not so easy. Okay. Okay, so now we go to work. So, so I was mentioning to you about when the electron is going very fast, you have these contraction factors. So this is a diagram of a periodic magnetic field. Here, for instance, you see the magnetic field is pointing up. Here it's pointing down. So what's happening with this periodic magnet structure is that the magnetic field is alternating down, up, down, up. It's a sinusoidal or approximately sinusoidal magnetic field. It's always in the vertical direction, but the amplitude is varying sinusoidally as you go through. The electrons are coming in with a very high energy. So at ESRF, the electron energy, that's the way I'll write it with a subscript E, is around 6 GeV, 6 times 10 to the 9th eV, and the gamma we saw before is like 12,000. So the electrons are coming through here, but when an electron feels a magnetic field, when it passes through a magnetic field, it has a Lorentz force, a V cross B force. So as the electron goes through, it's a velocity this way, a magnetic field vertically, and so there's an oscillation in and out of the board. That's the V cross B, okay? It's about as strong a force as you could get because the velocity is as high as you can get it. We're going to see that the velocities here are so close to the speed of light, it's like 1 part in 10 to the 9th. 1 part in 10 to the 9th. That's why these wavelengths are really compressed. And so the V cross B, the V is very high. The B in these periodic magnet structures is also very high, measured in Tesla or fractions of a Tesla. So anyway, the electron is going through. It's oscillating in and out of the board. Whenever a charge oscillates, it radiates, okay? If we were moving along with the electron, we'd just see it oscillating in and out, okay? But actually, of course, it's moving, okay? And in the forward direction, the radiated wavelength is going to be contracted substantially. Additionally, I'll use the letter capital N for number, some number like 100. So let's just say that there are 100 periods. This is one period. This is a half period, okay? So let's just say we have 100 periods. That means the electron, as an electron goes through, it goes through 100 cycles. If it goes through 100 cycles, it's going to produce a wave train of 100 cycles, right? Okay? No? Yeah, some. Okay. So, so the length of the undulator measured in periods will give us a wave train of a certain number of cycles. And I drew this little diagram over here because I didn't make up a slide. This is not about synchrotron radiation. This is about anything. If you have surface waves or any kind of oscillations, if you have some number of cycles, for instance, if you have 100 cycles, it says here of electric field, but it could have been anything, right? Pressure in a water wave. If you have 100 cycles and you analyze how accurate is the wavelength here, okay? If you do a Fourier analysis mathematically, you'll find that the accuracy of the wave in frequency space is going to be 1 over n. So if you have 100 cycles and then you cut it off, this is going to have a width of about 1%. If you go through 1,000,000 cycles, this is going to be 10 to the minus 6. So for instance, in a laser, where you have very accurate, precise separations between energy levels, it's quite common to get a wavelength of the laser of 1 part in a million, okay? Which means that it has a period, it has 1,000,000 cycles there, okay? So here is here's our undulator, we call it, okay? And the period is lambda sub u, the undulator, okay? The wavelength coming out to first order, not quite perfectly yet, is going to be this undulator period divided by twice gamma squared. So gamma here we saw was 12,000, so dividing by 12,000 squared, so about 10 to the 4th squared, 10 to the 8th, it's like a reduction of 10 to the 9th. So if you had a few centimeters here, the wavelength on axis would be those few centimeters divided by 10 to the 9th. So let's say it was 1 centimeter. It's actually going to be a few centimeters, but just to make the numbers easy, 1 centimeter divided by 10 to the 9th. So it's 10 to the minus 10 meters. So you're into your angstrom region, okay? The angle will be very small. It'll be in microradians. So if I showed you a laser pointer here, it would have, you would say, oh, that's a really narrow cone that comes out of this laser. It would be milliradians. Here, we're going to be talking about 10 microradians for the synchrotron. So sometimes we use the phrase that the synchrotron undulator radiation has laser-like properties. Seems to come from a little spot and it radiates into a narrow cone. Why is there a narrow cone? I'll get back to that in a moment, but the narrowness of this cone, the half angle, which we call the central radiation cone, this is where this 1% radiation I was telling you about, so this was 100, if this was 100 periods long, we'd expect the spectrum to be 1 part in 100. And this cone, the central radiation cone, is just containing that 1 over n bandwidth. The rest is outside of this angle, and we're probably not interested in it. And so the central radiation cone is 1 over gamma square root of n. So if the gamma was 12,000, let's say 10,000, and this was 100, so square root is 10. So we've got 10 to the 4th and 10 to the 5th. So it would be about 10 microradians, okay? So we're starting to get some feel for the numbers, okay? And the bandwidth in this radiation cone is this 1 over n. So I'll for sure stop for questions in a moment, but if you have a question now, please feel free. Okay? Yeah? Good.
So when you generate hard X-rays, you often need a high energy ring. So why don't you just use a smaller period in your undulator to
No, absolutely good question. So the question is, if you wanted hard X-rays where this is a very small number, why keep pushing this up so large? Why not just make the undulated period shorter? So rather than be a few centimeters, like 2, 3, 5 centimeters, make it a half a centimeter or something like that. And it's a technology issue. Just you need strong magnetic fields, and to get strong magnetic fields, you would have to push these things closer, closer. And it just turns out it's an engineering issue. We don't know how, we can't do it. But the question's perfect. Okay. So back to this thing before. So now we've seen our electrons are going through this periodic magnet structure. That's what's making them oscillate. And because the electrons are going almost at the speed of light themselves, there's this bunching, and it's a very, very strong effect. But this is an angle-dependent Doppler, right? So on axis, that's what we were concentrating on. It's a very short period, but the Doppler has an angle dependence to it. It's what you're used to from the train whistle thing. The train is coming at you, and on axis, if you're on the tracks, don't get hit by the train. But you have the shortest wavelength as the train is coming forward. But if you're off to the side, you don't get that Doppler shift, okay? So it's the same thing here. So if you're looking on axis, you see a very short wavelength. But if you look off axis, it's a longer wavelength. That's why I told you that the radiation was going to come out in 10 microradians, okay? This effect is so dramatic with these high values of gamma that the radiation cone, which accepts a small bandwidth, not great variations in wavelength, is a cone of only a few microradians. Okay? Does that? Okay?
So it's
Yeah.
a definition thing. You just define the cone as.
It is a definition thing. 1 over n is convenient, but it actually raises a good question. Why would we do that? So it turns out that a 1% bandwidth, generally not what we're looking for. If you're doing a thesis and you want to look at iron in a magnetic material or something like that, you probably don't want 1% bandwidth. You probably want something more like 1 part in 1,000 or 1 part in 5,000 or something like that. So taking 1 over n is like a starting point. We're actually going to use a monochromator after that to narrow it even further. But the number of periods in the magnet structure, that may be something like 50 or 100. But so it is a definition, and that cone angle goes with it. Great. So this is just redrawing this thing. So the shortest wavelengths, blue if it was visible, green and red off axis, okay? These are the formulas we talked about before. The value of gamma, it turns out there's an easy relationship that gamma is the electron energy divided by the rest energy of the electron. So it turns out to be this convenient number, approximately 2,000. So like for ESRF with the 6 GeV, the gamma is roughly 2,000 times 6, so just under 12,000. For Bessie in Berlin, this would be the number, a soft X-ray machine. And for Electra, it's approximately the same. Okay? What else? This is the relationship we talked about before. And this is just a conversion. Actually, I'll mention it to you. So laser people always speak in watts, milliwatt laser pointer or something like that, or a megawatt peak power or neodymium laser or something. But in the synchrotron world, we talk about photons per second. Okay? And so this is a conversion from one to the other. And it depends on the wavelength. How many photons there are in a watt or a millijoule depends on the wavelength. So this bracket means units. So if I told you that we had a wavelength of 3 nanometers, that means put the number 3 in here, leave off the nanometers, but just put 3. So for 3 this would be 3, and this would be now, the power would be, 1 watt would be equal to 3 times this, so 1.5 times 10 to the 16th photons per second. So that's how you use the bracket will, in my language, always mean don't put the unit, just put the number. Okay. So with synchrotron radiation, we'll encounter 3 kinds three forms at the synchrotron facilities. One with a bending magnet radiation, one a so-called wiggler, and the third and the undulator. And let me just peek ahead. Yeah. So I'll come back to that in a moment. Here's an example of a storage ring. This one's got 12 sides, I guess, or 8. 1, 2, 3, 4, 8 sides. But in general, all of these synchrotron facilities are regular polygons, so 12 or 20 sides or something like that. And inside each straight section, there'll be a periodic magnet structure, an undulator, like we just have been speaking about. But then the electrons need to be turned into the next straight section. And so this one might produce very short wavelengths, X-rays. This one longer, so it would be more in the extreme ultraviolet, 100 eV or something, good for chemistry, 50 or 100 eV for chemistry. Here it's angstroms for crystallography. But between each straight section, the electrons go through a single magnetic field or that turns the radiation into the next section. So here, it's a bending magnet. It just turns it through a fraction of a cycle. So rather than have 100 cycles, it has a half a cycle or a fraction of a cycle. If for this bending magnet turn, it only has a fraction of a cycle, what would we expect the bandwidth to be? So, right? Yeah, it's 1. Basically, it's, or even, right. So with the bending magnet, you've hardly got a full cycle. So this is going to be a very broad spectrum. So that's going to be the characteristic of the bending magnet radiation. And we're going to simply characterize it by what's called the critical photon energy. I'll come back with another slide in a moment. So this is the layout. And these modern storage rings have many straight sections. And they have a tightly controlled electron beam. What does that mean? It means they've made the electron beam as small as they can and the divergence angle of the electrons going through as small as possible. I might as well mention it now. Most of the rings are just now going through major upgrades. So as you've heard, ESRF has been shut down for a year. It's one of the first facilities to go through a major upgrade. Up until now, the electron beams have, as they're going through the structures, the electron beams have been about 100-to-1 aspect ratio. So it was tightly constrained in the vertical, but not as tightly constrained in the electron, in the horizontal. In the new rings, in the upgrades, the goal is to get something like this. Eliminate this. Why would you do that? Well, in many of the cases, like in microscopy, nanoscale imaging, we wound up throwing away this part. We could only use the middle part in our microscope. So we were throwing away 99 out of 100 parts to do certain experiments which required the brightest radiation or coherence, as we're going to talk about. So a lot of energy was being thrown away. Exposure times were 100 times longer. So there's a major upgrade going on now around the world. So Sweden led this at Lund. Now ESRF, the Brazilian ring, a new ring is just coming on. And it's basically the leading rings around the world are going through these upgrades to do this. So for instance, the ALS in Berkeley, where I worked, is doing this. But basically all rings are doing this because people, it's an engineering issue, accelerator engineering. People have learned to control the electron beam better than before. So probably other people will tell you more about this as we go on. So I want to go, oh yeah, and there's time structure. The radiation that comes out is not CW. It's not continuous. It comes in bunches. Generally, every 2 nanoseconds, there's a bunch. It has to do with how electron energy is replenished. When electrons go around the ring and they radiate, clearly the electrons are losing energy. Okay? It has to be replenished. And so there's a cavity with an axial electric field someplace in one of these sections that's oscillating. And for the electrons which have radiated the most photons, they've slowed down the most and they arrive a little late. And there's an axial electric field in a radio frequency cavity, 500 megahertz, that's pushing them back up with the rest of the electrons, okay? And that leads to this time structure. So this is showing the bending magnet radiation. So we were saying, since you only see it going through a small part of a cycle, it has a broad spectrum. This is what the spectrum looks like for a bending magnet. And we characterize it by a critical photon energy. This is a photon energy. It depends on, there's a formula for it here. It can be calculated, okay? And it depends on the magnetic field and gamma squared. But basically, this critical photon energy, just to give it a number, here, this is for Electra, has a 2 GeV ring, so we could figure out gamma. The critical photon energy is 3 kilovolts. What that means is that 50% of the radiated energy is on the high energy side, photon energy-wise, and 50% is of lower energy, okay? And this is showing you roughly how many photons per second come out, okay, in total. So for instance, at Electra, 3 kilovolts means that you could work in the soft X-ray. So it is a quote, soft X-ray machine. If you wanted a harder X-ray machine because you wanted to do crystallography, for instance, which you can do with magnetic fields, you might want to go to ESRF, which has a critical energy of 20 kilovolts. Okay? So you can get to the higher Z elements there. That would be important, and less absorption. What's interesting, though, is so that's the characteristic energy, the critical photon energy. But if you go out to 4 E crit, 4 times E crit, which here would be 12 kilovolts. So at Electra, it's a soft X-ray machine. If you were to operate at 12 kilovolts, you're only down a factor of 10. It's not the end of the world. So for instance, for people doing PhD thesis or competing for a little beam time, it's a little hard to get beam time on the undulators and with high brightness and coherence experiments. But bending magnets, there's lots of them. Every turn has a bending magnet. In fact, it probably has 2. And so it's easier to get access. And even at ESRF, you could get to 12 kilovolts. So you can do crystallography. At ESRF, 4 E crit gets you to 80 kilovolts. My goodness, what is it you want to do? Okay. So that's all I'm going to say about the bending magnets. They're easy to use. They're easy to get time on. They don't produce as much power, so your exposure times are longer. But they also don't heat up your optics, so they're a lot less expensive to build. Okay? So a lot of university teams have a bending magnet. Maybe they want to do some experiments later on an undulator, but they'll start in their own lab with some conventional source, laboratory source, maybe a bending magnet on occasion. Okay, so back to our undulator, which we've spoken about. And now is a good time to stop for water or questions or comments. Okay, so I haven't told you how to do the tuning. I told you about the electron goes through so fast, and you'll get a wavelength which is approximately the undulator period, which is typically a few centimeters, even up to 10 centimeters, divided by this. So I've told you that you can get that, but what if you want to tune it? Now I want to tune it to my particular absorption edges of some atom that's important to my PhD thesis, okay? So what you can do is you can raise and lower, close and open the jaw. So these things are a couple of meters long, and there's tons of weight here. So it's not a trivial thing, but people like here at ESRF and others have learned how to do this quite well. But if you close it down, you're going to increase the magnetic field on axis, so the V cross B term is going to be stronger. So the electron is coming in with a certain energy, and now it's faced with a stronger magnetic field. The V cross B is stronger. It's going to go further off axis, okay? And in order to execute its 100 cycles, it's going to take a longer time to do it. So closing the gap, increasing the magnetic field, causes the electron to take a longer time to execute its 100 cycles. That sounds like a lower frequency, a lower photon energy. So that's how you tune an undulator. And with a lot of undulators in the ring, everybody can tune their own. Each experimental station tunes their own, okay? So what is the formula, though, to do this? That we're going to spend a few minutes now to get this a little bit more precise. This is an approximate sign, okay? And it's true, but you'll be able to tune around that a little bit. So, but this is a shortcut. It requires the slightest understanding of relativity, which not everybody has had, but most of you will have had just enough to understand this. And what our goal is, by the way, is to find this formula. It's called the undulator equation. And it says that the wavelength is this lambda u over 2 gamma squared, which we were talking about. But this is the only term I told you about. Actually, I told you about the off-axis Doppler. That's this one. So if you're right on axis, theta equals 0, then that's what you get. But this is a measure of the magnetic field, the strength of the magnetic field. It's a non-dimensional measure of the magnetic field. Okay? And so this is your tuning term. So when the undulator is completely open, so the magnetic field is weak, let's say this is going to, if not 0, close to 0, then this is the wavelength that you'd get. Then as you start closing it down, you increase the magnetic field, and this non-dimensional parameter starts to peak up a bit. Okay? And we typically, excuse me, for undulators, run with k from 0.5 to several 3 or something like that. Okay? So we're going to try and get this formula, and so we do it in 2 parts. Here's our electron coming through, just to repeat the parameters. This is the undulator period. The electron is coming through with this energy. This is the relativistic contraction, Lorentz contraction formula, and is the total number of periods. In the frame moving with the electron is oscillating in and out of the board, and it radiates what's called, in that frame of reference, it's radiating in all directions. It's like a donut pattern, sine squared donut pattern. There's no radiation, this is rotated. The electron's oscillating in and out of the board, which here it's in the board, and there's no radiation in that direction. All the radiation is mainly off axis. Okay? This would be the same radiation pattern that you'd see for an AM or FM radio station. There's a big antenna. The electron's going up and down in this antenna, which you can see usually near a bridge or something like that, and it produces a dipole pattern. It doesn't radiate down to the ground or up to space. It radiates all around. Okay? So you get the same pattern here. So this is in the frame of moving with the electron. This is what you see. And the wavelength in this frame has been Lorentz contracted. As the electron was going through, it's like you're in the rocket ship and you see the meter stick contract. Here, it's the electron that's going through, and it sees this length contracted. It's contracted by this amount. Okay? That's so-called Lorentz contraction. So that's step 1. There's 2 steps. So in the frame moving with the electron is oscillating with this shorter wave. It's radiating, It's radiating with this shorter wavelength. So you've already had a reduction here of 12,000. But that's in the frame moving with the electron. But your sample is in the lab frame, and so there's a Doppler shift coming towards it. Okay? And the Doppler shift, if you go through the formula, this is if gamma was 1, this would be slow motion. Okay? This would be your Doppler formula. But relativistically correct, there's a gamma factor in there. If you look at the Doppler shift of this wavelength, and you put in this formula, this is what you get. It's almost our undulator equation. It's telling us that the wavelength we're going to see is this undulator period over 2 gamma squared, and this is the off-axis term. So we're not going to do the algebra here. I'm going to tell you, I'll tell you now, I've given you, first of all the slides are there for you to read. But if you'd like to read a little bit, if you go to the Hercules website, there are several chapters from a book a colleague and I have written. And there are chapters on synchrotron radiation and FELs associated with this lecture. And for the morning's lecture on optics, there'll be some more chapters. And you can find all of this algebra with paragraphs to read, make it easy. So for now, I would say just accept my rough explanations and get the concepts right. So you start with one gamma. There's a 2 gamma squared here. Why 2 gammas? One is moving into the frame of reference, moving with the electron. There's a Lorentz contraction. Then seen in the laboratory frame, there's a Doppler shift, and that gives you another gamma. That's where the second gamma comes. There's one from each of these things. So one from Lorentz contraction, one from Doppler. You get this equation. In doing this, we didn't take account of the fact that the electron was slowed down. It wasn't, we said this was gamma and the electron was shooting through at some velocity. But actually, as we played with the magnetic field, there's the loss of that energy through lateral motion, and it slowed the electron down. So we actually weren't going, the electrons were not really going through at gamma, with an axial value of gamma. The total energy in the magnetic field doesn't change, but some of the energy was going into lateral motion, depending on how strong the magnetic field was. And so there's actually a slowing down, as I was telling you. That's how the tuning worked, right? If you increase the magnetic field, it took the electrons more time to get through. The axial value of the velocity was slowed down. And when you take account of that, this non-dimensional magnetic field term shows up, K. Okay? So this is the undulator equation, and it allows you to figure out where you are with your magnetic field. And in practice, what do? You calculate these things and you figure out what you think you should do, but you stick some atom of interest, a copper sheet or something like that, and you play with the magnetic tuning until all of a sudden you see an absorption feature. Then you know you got it right. Okay, so that's how you actually in practice know that you are at the K value that you thought. Okay?
I have a question, sir.
Yeah, please.
With the undulator, we are just compressing the Bremsstrahlung in this direction, but we're not controlling this direction.
Lateral direction, no, we're not changing.
Then how can you say that the 4th upgrade of ESRF is contracting the wave in this direction?
You mean with these upgrades? So these are not controlled by this magnet structure. The size of the electron beam is controlled by other factors. For instance, in the ring, as the electrons are going around in the ring, so it's in a plane, every time they go through a bending magnet, the electron throws off a photon, right? And we know about the energy it's throwing off. There's also a little momentum involved. And so it winds up that the outgoing photon, okay, gives a little kick to the electron that did that. And that's what pushes it in the horizontal direction. So if, for instance, with the free electron lasers, you don't have circular motion. You just go down a straight tube. They don't have this problem. Their electron beam is just round all the way. But in the storage rings, as you're going around, every time there's a bend, you throw off photons, and there's a sort of a horizontal component of momentum. It's not a lot, but it's there. And so it kicks, and the electron, and so in a stable operation, you wind up having a long ellipse. So how do they fix this? They decide, okay, rather than have one at each turn, rather than have a single magnet, which gives a kind of a strong kick, let's have 5 magnets, each giving a weaker kick. And there's less momentum each time. And so they say they're having an n equals 3 multi-bend achromat, they call it. N equals 3, 3 bends, 5 bends, 7, 9 bends. And that really gets it down. So great. Thank you for the question. Okay, so I think this was a good part of what we're going to talk about here. Oh, I'm sorry.
One more question.
Yeah.
How much of the kinetic energy of the electron is actually radiated? Is the electron slowed down significantly?
No, it's slowed down enough, but we're talking about 6 GeV electrons, and we're gonna radiate a 1 keV or 10 keV electrons. So it's not so much, but they go around many times. But it's enough that you have to accommodate this. So there's an RF cavity that sort of the slower electrons get a little extra kick.
But
Good.
not inside one undulator?
No, it's constant, yeah. same question. Yeah.
What would be if we change the period between magnets in the undulator?
If we change the what?
Period between magnets. I mean, it's
Oh, yeah. Yeah. So if you change this period, so in each straight section there's a different undulator. So some have a certain period of, let's say, 3 centimeters, some have 5 centimeters, it depends. So for instance, the ALS, where the numbers will pop out of my head quicker, we'd have the people doing magnetic work, they would operate at around 700 eV or cobalt a little bit higher, and so they'll want a period of a certain amount to get the wavelengths that they want, okay? But the chemists, they want lower photon energies, 50 eV, they want and so they'll take a much longer period, maybe 10 centimeters or even more. Does that answer the question, or did I miss it?
I meant in the one undulator.
Oh, in one undulator. Well, if you did that, then you would have, let's say you did it in 2 pieces, okay? What the question is, what happens if you had one undulated period here and a longer undulated period? You would wind up producing a pulse which had one frequency in the beginning, the first part that they get to, and then the last part of the pulse would be a different wavelength. So you'd get 2 wavelengths coming out, okay? So basically we don't do it, or at least we try not to do it, yeah. But we put them into separate sections. But you could imagine that you have some chirp. You want, who knows why, you want some frequency which is shifting as a function of time. You could imagine doing this. Okay, yeah? Okay. Yeah, so now we have a sense of why we get X-rays, how we choose the photon energy, how we do the tuning. How many photons do we get? What kind of power do we get? So in general, you could think, oh, this is a complicated calculation. I'm going to have to read some advanced physics text on electromagnetic theory, David Jackson's book, for example, quantum blah, blah, blah. It's complicated, right? But actually, there's a way out of this also. And that is, I told you that the oscillating electron produces dipole radiation, and it's the same for AM and FM as it is for our X-rays. So it turns out that for anyone who took physics or electrical engineering, they know what is called the dipole radiation formula, that you get a donut pattern, a wraparound donut pattern. And this is what the formula is. The power radiated per unit solid angle depends on the acceleration squared and this angle, okay? This is the angle here. So this is the sine squared that gives it the donut, and it wraps around. Well, we could take our problem here, which is highly relativistic, and therefore the calculation would be complicated. And we said, well, if we're in the laboratory frame, in the frame moving with the electron, it's not relativistic. It's just a simple oscillation up and down. It's very much like the AM/FM radio. We know the formula already. This is what it is. So in the frame moving with the electron, this is the pattern, okay? And we actually know the power radiated in watts per unit solid angle, which we could convert to photons per second. So this part of the calculation is already known in the frame moving with the electron. Let's transfer back to the laboratory frame, so-called Lorentz transformation. They're just algebras, it's not a big brain strain. So you take this formula and you convert it back, and you will get that this power per unit solid angle gives us this formula. This is saying that the power, the bar means it averaged over a cycle, in the central radiation cone. So the power in that small angle, there was a power per unit solid angle. We're just going to take the part in the central radiation cone. It depends on gamma squared. It depends on the current in the machine, how many electrons are going by per second. And it depends on the current. Well, that's the current. So it depends on gamma squared and I. And this factor here, this is this magnetic tuning factor. Remember, this depended on acceleration squared. Well, in this structure, the acceleration depended on k. So this k squared is because of this a squared. Okay? This thing on the bottom is because I told you that when you close down the magnetic field and k gets stronger, you start slowing up the electron in its axial motion. And that winds up reducing the acceleration. Okay, it's slowed, it's going slower. So for instance, if you're in the small k regime where undulators normally work, let's just say you're at k equals a half, you can forget this thing. And you'll get that the power depends on gamma squared I and the magnetic field squared. Okay? As you increase the magnetic field, you'll slow up the electrons, and this will start to dominate at a certain point. For k, let's say if you go up to k equals 2, this is 4, so this is starting to dominate. So you'll see it in curves in just a moment. Okay. Here's our structure. Here's the formulas that we talked about so far. These two go together. The central radiation cone depends on this 1 over n bandwidth, and this is our magnetic field, non-dimensional magnetic field, K. Sometimes it's called a deflection parameter because it winds up giving the angle that the electron varies as it goes through. Okay? And this is a tuning curve. So this is power in watts, so we can convert it to photons per second, versus photon energy. This is at the ALS, which is presently at 1.9 GeV. This is the current. This is a kind of a long period, 8 centimeters. Okay? And these 55 oscillations. This is the tuning curve. So by opening and closing the magnet structure, you can tune with this device over this region from, let's say, 100 to 400 EV. A little bit of a surprise here is which end, when it's the weakest magnetic field, K is the smallest, which end of the curve are we on? Okay. Yeah, exactly. So when it's open completely, the electrons are going through the fastest. They're going through the 100 cycles. The acceleration is not so strong, and they're going through the fastest. That means the highest frequency. So when this is open, when K is very small, the electrons are going through fast, the frequency is the highest. So K equals 0 is over here someplace. Okay? And then as you increase the magnetic field, you start going up, and it goes up as the square. Okay? And then it levels off because of the slowing down, and it starts to roll over. Okay? This peak is at k equals square root of 2. We just take a derivative of that formula that we saw before. You take a derivative of this with respect to k, and you see that it peaks at square root of 2. Okay? One other thing, as it rolls over here, the lateral motion starts to matter in a way I don't have time to tell you about today, but you wind up producing harmonics. So rather than just have, let's say, 300 EV, you'll also have 900 EV. Usually the odd harmonics are the strongest. Okay? So that probably raises some questions, but we don't have time. I can say something if there's a question or later. Okay, so this is a summary of undulator radiation. Okay? And these are some tuning curves then. So this is for the ALS. This is the gamma value. These are all low energy machines. Gammas, these are soft X-ray machines. They're covering soft X-ray energies. This is the curve we've been talking about so far. They're reaching powers of about a watt. Okay, so this is the ALS, Bessie in Berlin, Electra in Trieste. Okay, and the next slide is going to be some hard X-ray machines. This is the third harmonic. So with the third harmonics, you can go out further. So people use the harmonics. I'll show you an example at some point of using harmonics to get to higher photon energies. Okay, and typically these are of order a watt for the soft X-ray machine. So what does that mean? Well, a watt. A laser pointer would be a milliwatt in a milliradian. This is a watt in 35 microradians. So this is extremely strong radiation. Okay, the power is a watt is relatively high power. Okay, and the angle is small. These are some of the hard X-ray machines: ESRF, APS outside of Chicago in the US, and Spring 8 in Japan. Spring 8 has the highest energy. It's 8 keV, so the gamma is very high. You notice they're all producing 10 or 20 watts in the central radiation cone, and this is their tuning curve up to, these are in keV. Photon energy is in keV. So here the fundamental is getting you up to, let's say, 8 kilovolts, but the harmonics will get you 3 times that. And the 5th harmonic, yes, hi.
So the profile of Electra seems very different. It's asymmetrical to on the last slide, previous slide. So the profile of the n equals 1 is quite different than asymmetrical compared to the other ones.
Why do you... You mean just because I ended it here and I didn't end it there?
I just didn't see that the x-axis was logarithmic.
Oh,
Okay, yeah, so never mind.
I see. Well, you caught me because I didn't notice it. Okay. Went the wrong way. Okay, and so these are various synchrotrons around the world, and they're where are they, and what are their photon energies, and the question. So, you multiply by 1957, approximately 2000, and you get the gamma value. But these are all big-time facilities, right? And the new giant in the game is Petra 3. Okay. Okay. Oh, so we're going to take a break in just a second. On each beamline, there's what's called, on each of these, for each undulator or bending magnet, there's what's called a beamline. And what does the beamline do? It takes that 1% of radiation and probably narrows the spectrum. 1% is almost always too much, too broad. Okay? So you want to put a monochromator on it to narrow it down to some degree. Not always, but almost always. And you also need to get the photons out of the sample, out of the undulator. The angle of emission was microradian, so it seems quite small, but you wind up having to go pretty far away. Why do you have to go so far away? You go maybe 10 meters away before you put your sample. One of the reasons is that the radiation coming out, let's say at ESRF you've got 10 watts and 10 microradians, you're going to burn a hole in the first mirror you come to. So they wind up using water cooling or other techniques to carry away heat, and various aperture techniques, but you wind up, your sample is a long way away, so your beam, even though the angle is small, it's expanding, and you may want to focus it down to nanometers or something like that, certainly to microns, because of your sample structure. Okay? So you wind up introducing a monochromator, an entrance slit, some grading, which you might change depending on the photon energy, and an entrance slit, exit slit, and then onto your sample, and there will probably be some mirrors to re-image this radiation onto your sample. So there'll be some imaging part of this and some spectroscopic monochromatization that goes on. So that's in the so-called beamline. Okay, and this is what one looks like. Maybe 10 meters long. This is an ALS beamline. So it would be starting down there. Oh, this is not a pointer. Starting down here would be the undulator, and this might be the vacuum vessel where you put your sample. Okay. And you can do a lot of different science by having different undulated periods in the different straight sections, and also using the bending magnets in between. So typically you have hundreds of people working at any given time, many thousands over the year. Oh, so coherence. I wonder if I should take a break now. Why don't we take a short break now, and when we come back, we'll talk about what is coherence, why do we care about coherence, and what is the role it plays between an undulator and a free electron laser. Okay? And I'll explain this. Okay? The thing, you can take your break now, but the thing to note is that this is a marching band. This is actually from Barack Obama's inauguration parade in Washington, But notice the footsteps. They're all stepping precisely as the others are. Everyone here is putting their foot down at the same time. They are marching coherently. Okay? We want our photons to do that. Okay, let's take a break. Probably not. I showed you tuning curves, okay, which were plotting power in watts, or photons per second would have been equivalent, versus photon energy maybe in keV or something like that. And I showed you this tuning curve, okay? And I said that this was k equals 0, this was peaked at square root of 2, and this is higher values. And there was a line here, and what this is narrow spectrum. So we're producing, out of the undulator, we're expecting to get a bandwidth of 1 over n. So this is the 1 over n. This width is 1 over n, so maybe 1% or something like that. And that by the tuning curve, it means that as we change the k value, this thing moves. So for k, when it's completely open, you're over here someplace. And then you start closing it down, and this is moving. Okay, and you close it further, and this is moving over here. So in that sense, it's a tuning curve. You're not getting a broad spectrum with an undulator. You're getting a narrow spectrum, something like 1 over n, so 1% or 2%. But you can tune it by opening and closing it. So that's what was meant by the tuning curve. So is that resonant? Yeah. Okay, so this is this marching band. I used to have marching soldiers, but my wife told me that was a bad idea. Let's get so there's a person here, and he's doing what's called cadence. He's counting. He's doing this noise, usually with his foot, or making some noise with his mouth or something like that. And every time he does that, everyone is supposed to put their foot down. So that's why these guys are all marching coherently, in phase, we could say, okay? And there's some coherence length that goes with that. You know, if it's a still, quiet day, not a noisy crowd, everybody in this group can hear this man, and they're all marching in phase. But suppose it's a noisy crowd. The people on the far side may not hear him so well. Maybe there's a wind blowing, okay? And so it may be that people within a certain distance can hear him quite well, and they're marching in phase, and others aren't quite getting it right, and they're starting to get out of step, okay? So that's a coherence length, okay? So now we just have the concepts of coherence and coherence length. Now we want to do the same for photons, okay? And there's a large mathematical studies of coherence, because you want to be quantitative, not just a coherence length, but what's the expectation that this person will know when to step, 80%, and this one is 70 and 50. And so there's a quantitative study of coherence. We're not going there. We're just going to get the concepts right today. Okay? So in general, this is the mathematical part of it, okay? What is the expectation, the complex coherence factor? This is some numerical value you're going to get, depending on the expectation that if you knew the electric field at one point, what's the expectation you'd know it at a second point, at the same time or a different time? So for instance, if you could measure the electric field here, what's the expectation that you would know it here? So we're not interested. For us, we're interested in, can we form interference patterns? That's why we want coherence, okay? And we want to be able to focus to the smallest spot or produce spherical wave fronts so that when we do diffraction or scattering, we know the angles quite precisely, okay? That's what we're in. So in general, it involves interference effects. If we had some wave that's propagating along rather than in the spherical sense, maybe there's a lens that collimated this radiation, we will in general have radiation in this narrow cone, and we'll be interested in what are the coherence properties to the side, lateral coherence, and longitudinally or in the time direction. And so we'll talk about a longitudinal coherence, that's this, longitudinal or sometimes temporal coherence, and this we'll call spatial coherence or transverse coherence. So that we're going to treat them separately. This longitudinal coherence will depend on the bandwidth, the wavelength and the bandwidth. Okay, and this one, it will depend on, was the source that radiated this a point source or close to a point source? A point source, you can imagine, if it's really a point, it looks like a point source. It looks like it because it's radiated spherical waves, and we don't see any wiggles on the curves, on the radiated wavefronts. If we see a lot of modulation, then it clearly didn't come from a point source, right? So in the limit, we would like a point source in order to get all of the photons across the wavefront to be radiating in phase. Okay, so we will find, or I'll just tell you maybe, and you'll read if you're interested, that in this direction the coherence length is lambda squared over 2 delta lambda. A way to see this is if it's lambda over delta lambda, how many waves of coherence are there, right? 100 waves multiplied by the wavelength. So if I told you you had a wave train of 100 cycles and the wavelength for each one was 1 centimeter, it'd be 100 times 1 centimeter. That's what this is, okay? The factor of 2 is a definition issue, okay? So it's lambda over delta lambda times lambda. That's giving you this. Is, for instance, you could have had a wave train which was just 100 cycles with some wavelength, and that is the temporal coherence length, okay? So if you're making a little hologram in a laboratory, you need a laser which has this kind of temporal coherence. You need everything this way laterally to make a hologram or a good interference pattern. You need to satisfy a different condition, which is that the diameter of the source multiplied by the opening angle, this is actually a half angle, is roughly equal to lambda. Lambda, if these are Gaussian quantities, RMS Gaussian quantities, this is the formula. If we wrote this in terms of full width half max, which is what we do in the laser world, the diameter times the half angle in terms of full width would be just lambda over 2. Easier formula to remember. And I will show you some examples where we use this. Okay? And if we just use this formula as I just said it, you'll see it becomes pretty trivial. So here's our coherence length in the longitudinal direction. And basically what I'm showing here is the solid line has a wavelength lambda, okay? And there is some spectral width here, though, okay? There's a central wavelength, that's the solid lambda, but there's some spread there. And so there's some spread in wavelengths. And if you go a certain distance, these things become out of phase. They're no longer adding in phase. And so I'm going to arbitrarily say when these things get 180 degrees out of phase, I'm going to call that the coherence length, okay? And this is some algebra. No use me taking time to do it. If you're interested, you read it. But going through this simple little bit of algebra, you'll find that the coherence length is lambda squared over 2 delta lambda. And the 2 just comes by how I define this, okay? Depends on your application. Okay, so that's in the propagation direction. You have all the slides, and you have some reading material. You can read with paragraphs and lots of words, so it's easier to digest. In the lateral direction, how do we get in the limit? Let's just, for this class, let's just worry about how we get the spherical wave, which is in the limit. That is, we want it to appear to come from a point source, because a point source radiates a sphere, okay? And so we're going to associate full spatial coherence with a spherical wavefront. That seems simple enough. And a spherical wave implies a point source. So now we just have to figure out, for the wavelength of radiation we have, how small is a point source? Okay? So if we're talking about microwaves, microwave ovens or something, and we want to do an experiment with coherent microwaves, we'll probably have to put a small aperture in front of our microwave oven and then let the microwaves come out. But we could take a guess at how big that aperture would have to be, right? So we have to open the door. Somehow or other we poke a hole in the door of our microwave. It's probably going to be a microwave length, a few microns or something like that, okay? For X-rays, we're going to do the same trick. We're probably going to wind up using smaller diameters, microns. So how do we figure this out? Actually, the simplest way to do it is from Heisenberg's uncertainty principle. So I guess some fraction of you know what Heisenberg's uncertainty principle is and some don't. But basically, it's a statement that says the uncertainty is associated with position and momentum is h bar over 2. Okay? So Werner von Heisenberg. And if you convert this into a photon situation, this expression gives you this expression. These were Gaussian uncertainties. Uncertainty in position, uncertainty in momentum. So for a photon, momentum is h bar k, k being 2 pi over lambda. These are uncertainties, products of uncertainty. So this is the uncertainty. Uncertainty as to where the photon came from, somewhere within this diameter and somewhere within this angular cone. Okay? So for those who are interested, this is how you go from Heisenberg's uncertainty principle, where again, these are RMS quantities. P is the momentum of the photon. So I'm looking at a diagram like this. This is my source. I don't know where the photon came from, top, bottom, or whatever. So there's an uncertainty here, and there's an uncertainty here as to what angle it came out at. And if I replace the P momentum by h bar k, uncertainty, uncertainty, and k by 2 pi over lambda, I'll get this relationship. This algebraizes. And this is what I'm calling the diameter, the uncertainty in origination, the uncertainty here in half angle, and if you just, this is the d, the theta, lambda over 2 pi. Okay? If these are RMS quantities, so which accelerator physicists like, but laser physicists like full width at half Mach. So if you take this formula and you write it in terms of full width at half Mach, it becomes lambda over 2. So for instance, we were talking about in X-ray cases before where we said we have a central radiation cone, let's say for hard X-rays here at ESRF, where this was 10 microradians. The cone angle coming out was 10 microradians, and the wavelength, let's make it a nanometer. It should be an angstrom. If you put in an angstrom here as a wavelength here at ESRF and a 10 microradians, somebody in the room figure out what the diameter is. But I can tell you it's going to come out to be some microns. So well, here, maybe we should just do it. So we have d dot theta is lambda over 2, and lambda was an angstrom. Let's make it 2 angstroms so the 2's cancel out. So lambda equals 2 angstroms, which is 2 times 10 to the minus 10. So, and this is going to, so we're going to have that d is equal to, it's going to be 10 to the minus 10 meters. The 2's canceled out. And the theta we said was 10 microradians. So that's 10 to the minus 5, right? 10 microradians, 10 to the minus 6, or 10 to the minus 5. So this is going to be 10 to the minus 5 meters, which is equal to 10 microns. So if you take one of the undulators out there and you put a thick foil and drill a hole of 10 microns in diameter, the radiation that comes out will satisfy this, and you will have the spatial coherence that you would have from a laser, and you can make holograms. Okay? If you don't put the pinhole there, you won't get the fringe patterns, you won't get a hologram, right? You can still probe matter, but for instance, you couldn't do experiments that require coherence and interference. So for instance, a so-called transmission X-ray scanning transmission microscope, where you want to focus the radiation from an undulator with a zone plate to the smallest possible spot size and then raster scan. So you're making a probe here, and you want the spot size here to be as small as possible. Then this wavefront has to be a spherical wavefront. If it's not, you're going to get a bigger spot size. So this requires spatial coherence, and it requires you to put a pinhole in there. And that's how you do the calculation. So they're usually in microns. Okay. And you could do some standing wave experiments where you have light coming and reflecting off a surface and going out. So it's X-rays coming in, going out. And the incoming wave and the outgoing wave interfere with each other, and they produce a standing wave. If the wavefronts are perfect, if it's coherent wavefronts, you'll have interference like this, and you will get standing waves. And by changing the angle, you can move the standing wave pattern up and down, and you can use it to probe, let's say fluorescently probe, some material that's on the surface. So it's another example of using coherence. A student I have been involved with for many years did his PhD thesis on Indus 2 in India, which is not known for its coherence properties, but he got these ideas straight, and he did this as a PhD thesis. Okay? And you can make off-axis holograms. Okay? You need coherence to make a hologram. It's an interference experiment. In this case, is undulator radiation. A pinhole was used. It was kind of big, 20 microns, but it was soft X-rays. And that wavefront illuminated an aperture that had a little tiny pinhole that was going to be the reference wave, also launching a spherical wave, and a somewhat bigger hole where there was a magnetic material placed there. Okay? Some radiation came through the magnetic material. Some radiation come through the reference. These waves interfere, and they produce an off-axis hologram, which could be reconstructed, and this is the kind of wormy pattern that evolved. If there's anyone here who's interested in X-ray holography, there's been a really great example of this recently, and I realized last night I'd never put a slide in to show it, but this Russian woman who works now at Stanford at SLAC did a really marvelous off-axis holography experiment using the free electron laser there. Okay, the people who did this, these are the authors here. The first three were PhD students. Yeah, I'm sorry.
Yeah, I'm sorry, I just don't understand why do you lose your coherence, for example, if you make the hole a lot bigger?
I'm sorry?
If you make the hole, for example, a lot bigger than the 10 microns, why would you lose coherence?
Yeah, no, good question. So why the question is why, if you made the pinhole bigger than what we just estimated, basically we're associating a point source. Point source produces a spherical wave. So if you have a couple of point sources nearby each other, they're each producing a spherical wave, and they add up in the far field, and you get some wobbly wavefront. Not what you want. So the question was, well, how small should that pinhole be? So we used this formula to say, okay, if we got to 10 microns here, then we should get a spherical wavefront. If we make it bigger than that, we're going to get a wobbly wavefront. And the interference patterns, rather than having a high modulation, have a modest modulation. Okay. Anyway, so these first three, Stefan Eispit, Jan Luning, and Bill Schlatter were graduate students at the time, and they got the front cover of Nature, and they all got great jobs out of this. Yeah, so, right, so they're directors of facilities now. Oh, I'm sorry. We took our 10-minute break. So this now has to do with this business of a pinhole. So yeah, we're just about out of time. So actually what's going to happen is I'm going to continue this lecture tomorrow morning, and then I'm supposed to do optics, X-ray optics, and imaging tomorrow, but that doesn't take as much time. So we'll go for a few minutes here and get through this coherence issue a bit. So here's an ordinary light bulb. It's radiating in all directions with all colors, right? Shown as just having two colors and going in different things. And this is from Arthur Charlot's article on laser light shortly after he got the Nobel Prize years ago. He wrote an article. And so here's a light bulb that's radiating all over the place. Here's what happens if you put the pinhole of the right size, by the formula we just talked about, to get the spherical wavefront. And this separately is if you put a filter or a monochromator to choose just one wavelength. So here there were only two wavelengths shown. This is filtering out to get only one color, one wavelength. And here, the two of them are put together. You put a pinhole and a filter, and now you've got spatial and temporal coherence. Now you can make holograms. Difficulty is you won't have much power because you're blocking most of it, right? But so the laser came along. That's what Charlot and others got Nobel Prizes for. And actually, you put the pinhole inside the cavity of the laser so you don't lose power. You only amplify light that can go through the pinhole. It's a trick. I could tell you more. But basically, in the laser, you put the pinhole in. So for us, synchrotron radiation, undulators, we put the pinhole in the front, and we go from a watt or 10 watts, we go down to milliwatts or even microwatts. We can still make holograms with short exposures. But the free electron lasers have now come along, so you're going to hear about them. And it's the equivalent of having the pinhole inside. What they do for the free electron laser is they start with an electron beam which satisfies this criteria. It satisfies the d dot theta equals lambda over 2, and that's all you amplify. So the free electron laser takes you from watts or tens of watts to gigawatts, tens of gigawatts of power, and it's all spatially coherent. So it's one of the reasons I want to tell you a little bit about that. So with the synchrotron radiation, we'll actually wind up putting the pinhole and the monochromator. Free electron laser, we won't. So I'm going to show you just a few slides, and I'm going to go through quickly because we're basically out of time. But what we do is we take our undulator, we put a pinhole, an aperture which just chooses the central radiation cone, so that's the 10 microradians or so many microradians, and the pinhole around 10 microns or something like that, and what comes out looks like this. This is the signature of coherent radiation. This is the central lobe of radiation, and because of diffraction from the edge of the pinhole, you get these other rings, but this would be the middle. This is extremely bright. This would be our spatial filtering. So we actually do that at the synchrotron. So we have a complicated beamline. We have tuning curves, and whoops, I didn't see what I was looking for. Anyway, this was part of a PhD thesis for Christine Rosefjord at the ALS, and she produced this coherent radiation, and she used it to probe materials. And but this is just, I think, enough of that. Here's an example with hard X-rays at the APS outside of Chicago, and this is the tuning curves that they start with, but they wind up getting spatially coherent radiation in a very narrow bandwidth because they use a crystal monochromator, and they wind up getting these levels of power. Okay, and I think that's where we're going to stop. Yeah, so when we meet again tomorrow morning, I'll start you on what's the difference between an undulator and a free electron laser. That's where we'll start. Okay, thank you so much. Let's have coffee. Yeah, I put this up. I want to review a few slides. For the person in the back who asked yesterday, is it possible to split this? And I said, well, yes, but we don't do it. I realized afterwards, actually, we do it. So in some cases, for instance, at the Advanced Light Source in Berkeley, and I would imagine at other facilities, they cut this in half, make 2 different undulators with 2 different undulator periods, and they put a magnetic field here to just direct the electrons into the next one. So it's not much of an angular difference, but over many meters, it's enough that you can have different vacuum chambers in different experiments. So you each get half the power, but you each have your own undulator, which you can tune separately. So we do it. Okay, any questions or comments? It's good to start. Something I should address. Okay, I'm going to go over a few slides from yesterday. And you're welcome to comment, okay? So this was our visual of how we're getting X-rays. The electrons are going through some period, through some undulator with a period of a few centimeters. So how do you go from centimeters to X-rays, right? The electron is going through, it's oscillating. So you would say, well, wait a second, why isn't the wavelength 3 centimeters then? Okay, so it's not. And the reason is because as the electron is oscillating and releasing its wave fronts, the wave fronts are just bunching up. And they're bunching up on axis, and as we saw, I'm going to re-show that same slide. Basically, you get very short wavelengths on axis, but off axis, because of this is a Doppler shift, okay, off axis the wavelength is longer. So when you only look at X-rays, for instance, or if you put a small aperture in front here, you'll get the X-rays on axis, and off axis it rapidly becomes some longer wavelength. This is what, and so these wavelengths are so short, these things are so close that just going slightly off axis, a few 20 microradians off axis, you're already into longer wavelengths. So that's, one is the physical mechanism. What, I'm going the wrong way. Yeah, so this is, everything's in the forward direction, okay? And we had bending magnets, we had wigglers I didn't talk about so much, and we have the undulator. The angle here is very small, the angle here is very broad, and the spectrum is very broad. The wiggler I didn't tell you about because of time, but basically here you get a certain kind of X-rays. I told you there was a critical photon energy, which for ESRF got you up to 10 keV or more. You can't increase the magnetic field here though, or the electrons will crash into the wall. Okay, so there's a limit on what you can do with the bending magnet. But with a wiggler, you could actually make a stronger field. A wiggler is like an undulator, but it's only a few periods, and the period is long. You can make the magnetic field much stronger, let's say twice as strong, and before the electrons hit the wall, you come to the other side and you go back. So you manage not to hit the walls with a stronger magnetic field. You only have a few periods. Basically, this is a frequency shifter. It takes this same bending magnet radiation and pushes it out another factor of 2 or something. So in the old machines, storage rings, people who were trying to get to harder X-rays for crystallography or material science, they would use wigglers. They're not used so much. And on the newest machines, they're probably not going to be used. Okay, am I going the right way? No. Yeah, so this was the critical photon energy. Half the energy on one side, half of the energy for a magnetic field. This was our undulator equations, our undulator diagram, okay? Short wavelengths on axis within a central radiation cone, which came into microradians, okay? And with a bandwidth 1/n. 1/n generally like 1% or 2%, just too broad for the experiments most people will do. So you wind up putting a monochromator in there, crystal monochromator for hard X-rays, glancing incidence reflection monochromator for soft X-rays. And this was another key slide, and that is that how do we get to these very short wavelengths? Okay, we say that actually for the electron coming through here, it sees a Lorentz contraction. This is like the meter stick, and the electron is coming by at this high value of gamma, and it sees a contracted period. And this is the contraction. Whoops, where did it go? This is the contraction. The electron, in the frame of reference of the electron, it appears that the length, the frequency that it's oscillating at, is this lambda u divided by gamma. So that's a big change. Remember, this gamma is very high. So that's a Lorentz contraction into this frame. And then we have an oscillation, which is a dipole radiation. This is a non-relativistic calculation. So we again manage, in order to calculate power, we do the calculation in this frame where it's non-relativistic, and we get this so-called dipole radiation. We can just use that and get the power out of it. But anyway, this is in the frame moving with the electron. In the laboratory frame where our sample is, everything is Doppler shifted towards it. This source is coming at it with this wavelength, but in the laboratory you see it Doppler shortened, and you get another factor of gamma. So now you have that the wavelength is lambda u over 2 gamma squared. And because of the off-axis, this is the off-axis Doppler shift, okay? And when we account for the fact that the electron actually, in coming through here, because of the magnetic field, it's going off axis, that's the oscillation that's producing the power. Actually, the stronger the magnetic field, the more it goes off axis. It takes a longer time to get through. Okay, so it's a higher magnetic field, make it a lower frequency, longer wavelength. And I didn't show you how to do the calculation, but I gave you some electronic copies if you go to the website, and you can read about this and just go through the algebra. It's just algebra, and you'll see that there's a magnetic tuning factor, this non-dimensional K, which for those who came earlier, I was pointing out, was introduced. This formula with this capital K was introduced by a graduate student at Stanford named Brian Kincaid. Okay, so some motivation. Okay. Yeah, the power calculation, this dipole radiation is just well known for electrical engineers and for physicists. It's the same as any kind of oscillating electron, whether it's in the radio frequency wave or the visible or the X-rays. And so in the frame moving with the electrons, we use this formula, and then we do what's called a Lorentz transformation of all of this back into the laboratory frame. And this is our formula, that the average power radiated within the central radiation cone depends on the acceleration squared, the current, and gamma squared. Okay? So can someone make a comment? This is totally baffling. No? Yeah?
Quick question. Here you only use sort of a classical representation of your electron.
I'm sorry?
You use a kind of classical representation of your electron with like a particle point. How would it be with like a quantum wave function
Yeah.
with Heisenberg and uncertainty principle and so on?
So the uncertainty principle we are going to use, right? It's a very powerful tool. But just a quantum mechanical calculation or relativistic electrodynamics, there are several books out there. Maybe I can reference them to you. But I find that you could not possibly teach a class using those techniques, you know, unless you're just speaking to specialists. So I prefer these other techniques, which are moving around, you know, using the best of the semi-classical interpretations. Okay, so this tuning curve, by the way, some people caught yesterday. So these are the equations and everything, and I said this is the tuning curve. This is how much power you're getting at the different photon energies. But this is a tuning curve. This is actually what you're going to get. You're going to get power, let's say at 200 eV, but if you open or close, this line moves along here. So you're only having this, you're not getting this whole curve at any one time. So for instance, if you open it wide, you're down to small k, this line would be over here. And then as you close it down, this line is moving along, okay? So that's the tuning. You're opening and closing this thing, and this line is moving under this curve, and it's showing the peak, okay? And I think maybe that's all I really wanted to say. Yeah. Okay, so we talked about my marching band. So this was when Barack Obama had just become president. They always have a parade in Washington, and this is the marching band from the parade. And I had told you that for radiation, to get everybody in step, to get all the photons in phase, so that they're all producing more or less the same wavelength, but they're not in phase with each other. And in an electron bunch, there's something like 10 to the 8th to 10 to the 9th electrons, and they're all going through this undulator, so they're all more or less radiating at the same wavelengths, but they're completely out of phase, and they're moving around randomly, so their electric fields are not connected to each other. So what you see, you wind up calculating the radiation from a single electron and then multiplying by 10 to the 8th. That's all you get. You just multiply the radiated power from one. Okay? When the free electron laser comes along, we're going to see that's not what's going to happen. We're going to add the electric fields, and power, in any case, not just for X-rays, but the power is proportional to the electric field squared. Okay? So wherever you can have the electric fields adding, you can gain a lot. If you have 10 to the 8th or 10 to the 9th, let's say, electrons radiating in phase, all of a sudden you get a gain of 10 to the 8th or 10 to the 9th. So what we're going to see now is that rather than get powers of a watt or 10 watts, we're going to get gigawatts. So the FELs produce gigawatts of power, lots of energy in a very short pulse, femtosecond pulses. So we're talking about spatial and about coherence, both the temporal coherence or longitudinal in the propagation direction, and this is the coherence length. It's coherent over what distance? It's lambda over delta lambda, so that's the sort of the 100 cycles multiplied by lambda. So that's the coherence at length in this direction. In the other direction, in order to have full coherence, you have to satisfy this equation where d is the source size. So it could be the electron bunch size, or it could be a little aperture in front of it. Okay, and some angle that you collect, which would be, if you want all the X-rays within the central cone, this could be the central cone angle. It doesn't have to be, but that's most commonly what we do. Okay, so if you combine these things, if you meet that condition, you'll get coherence over the whole wavefront. Now you can get the electric fields adding up. And so we went through this, and we did use Heisenberg's uncertainty principle as in this case. I use it in other cases also, but basically we used Heisenberg's uncertainty principle to say, okay, if I want to have a nice spherical wave, full spatial coherence, how small does this have to be? And it comes down to uncertainties. A way to do it, it's not the only way, but it's a simple way, is to say that this is an uncertainty of where the photon came from, okay, and what's the limit, and you wind up with this expression, okay. And again, if you're interested in these things, go to the Hercules website and download just chapters of the book and read. Each chapter begins with just some paragraphs, just words to get the ideas across, and then slowly introduces you to some mathematics. Yeah?
This means that in an undulator, the length of the electron packet is too long to have constructive interference at the end of the undulator?
Absolutely, yeah. Basically, so the question is, in a normal synchrotron radiation, the electron beam has some size coming through, a diameter, let's say, of the bunch coming through, and it has some divergence angle, which we call the central radiation cone. And if you take that diameter, it's too big. It's way too big. Maybe it depends. You know, the electron beam is actually elliptical. It's very wide in one direction, the horizontal, and not in the vertical, in the present synchrotrons. Okay? So in this lateral direction, it's way too big. In the vertical direction, it's kind of in the ballpark. Okay? Okay, so we talked about the fact that you could introduce a pinhole and a monochromator, or you could put all of that inside and have a laser and get some coherence. And so this is an example from a PhD thesis where it was undulator radiation. The beam is too big, as you're seeing, but if you put a little pinhole there and you capture just the central radiation cone, so I'm choosing the angle, satisfy this condition, you get this beautiful coherent radiation. Okay? And you can make holograms and interference patterns of any kind you want within this region. Okay?
I have a question.
Yeah.
So, like, I understood that we use the pinhole to get the center, like you have this representation of color codes of the
Yeah.
wavelength, so
Yeah.
we get the center part.
That's right.
So I'm still unclear about these phases. So you said like each of them
Oh.
discussed yesterday, and we're still not clear about it.
Right.
So
So
10 to the power 8 electrons,
Mhm.
all of them radiating at their own way, and then ultimately what I want is a coherence, right? So how
Right.
does this pinhole include that part too, or
Yeah.
it's just the central core?
you're on to the matter before us. So the next few slides are going to get into this, and I'll say more. You can ask the question again after that. It'll be a good time. So this is what we've been talking about so far. This is our undulator. This is exactly the question. There's all of these electrons, and they're moving around, right? they're moving around randomly and all over the place, and each one of them is radiating. But because if you're averaging over just a few cycles, which for X-rays is not very long, the electric fields are not adding up in phase. Each one of them is just radiating separately, completely separate from the others, okay? And we calculate the power from one, and we multiply it by how many there are, 10 to the 8th or 10 to the 9th. And when we do the calculation, we use F equals ma, mass times acceleration. So the force is mass times acceleration. That's how we do the calculations. But so this would be your mass times acceleration, right? But this is the Lorentz force. And in this, for the undulator, we said the force was V cross B. V is the speed of light coming this way. B is the magnetic field. There is no applied field, okay? So we don't calculate. So we just leave this out, okay? But that changes when we get to the free electron laser. In the free electron laser, there's a couple of things. One, it's much longer. This was perhaps 3 meters or 5 meters long. This is perhaps a half a kilometer or a kilometer long, or 2 kilometers long. It's really long. This one had a certain current. This one has a lot more current, which means there is a certain number of electrons in this bunch. There's a lot more electrons in this bunch, okay? And what else did I say? Oh yeah, here the electron beam is kind of big. So currently it's highly elliptical in all of the rings, but they're just coming down to closer to a circle. So ESRF is one of the first. Sweden, Lund, Sweden, where they have Max 4, they were the first one to go from this highly elliptical beam to somewhat closer to a circle. Now ESRF, all the other facilities, leading facilities, are doing the same. But at any event, for the synchrotrons, this beam is too big. And we were saying we're going to put an aperture in front of it. For the free electron laser, this is meant to be smaller, but I couldn't make it too small. This goes here. You have a smaller electron beam, so it satisfies this condition, d dot theta equals lambda over 2 or lambda over 2 pi. It solves it automatically. The radiation is automatically meeting this condition. It's still, there's a little miracle that happens here, though. It's gone from this random location of all of the electrons in the bunch to something which eventually, at the end, looks like an electron wave, something like this. Okay? And now, in this case, all of the electrons are radiating in phase. Here they were radiating random phase, here they're radiating in phase. So the question is, how did this happen? So I think you're going to have other lectures on free electron lasers, but I thought it'd be good to get the concept straight about how does this happen. So what happens is, this is just starting out here, but with higher current and smaller size, and this starts to be a little micro bunching, a little modulation here. And then as it goes along, the modulation gets better and better and better, okay? And the question is, how did that happen? And that's what's going to make this a free electron laser, which is different than the conventional laser. So these are the 3 things that you need. Am I going backwards again? Yes, I am. Okay. I'm just repeating this diagram you saw before. This is what you saw before at the end. Notice that here I said neglect the electric field because there is no applied electric field, and the electric field from the random charges, not important. Here we leave the electric field in because now all of these electric fields are adding in phase, and although it's still kind of weak, it's what provides the feedback to make the lasing process, okay? So all this says is there's what I call micro bunching takes place. This was a bunch. These are like micro bunches, okay? And the electric fields here are chaotic. They don't add in phase. Here, the electric fields add in phase, and because of that, the electric fields adding in phase, we're going to get this extra factor of however many electrons there are in the bunch or within one wave. And so we're going to get this extra factor of n squared. N squared is a phrase physicists use whenever they're talking about coherent properties. They went from n times the power from 1 for the incoherent process up here, n squared down here. So whenever we have a coherent process, you hear us say n squared. Ooh. Well, the only thing I really want to capture out of this is that with the undulator alone, you had watts or tens of watts of power. And because of this n squared effect, we're going to get to gigawatts.
One question.
Yeah.
You had a larger synchrotron with larger undulators. You could get the same effect for the synchrotron as the free electron laser because the electric field is the one produced by the bunch of electrons. So if you had a sufficiently big synchrotron, you will have the same effect?
So this is a good question. So why don't you just get the same thing with a bigger storage ring, a bigger circular machine, right? The question is, could you get the same thing with a single? So first of all, you have to make the undulators long, like a kilometer. Okay, so it's getting long. The other thing, yeah,
Of course, but
it's
theoretically would be
the mathematics of the undulator to the FEL is the same. And when we analyze the free electron laser, we use the same equations, the same undulator equation that we did before. We calculate the power the same. So in a sense we do, but this time I do want to go backwards. You do need these three things. You need a longer undulator, you need a higher current, and you need a smaller electron beam. If you do all of those things, you're going to get some amount of lasing. So maybe you won't get gigawatts. Maybe you'll get, I don't know, hundreds of watts or thousands of watts. So in principle, what you're asking, is it possible? Yes, it's possible, but you need to do these three things. Not enough? Yeah. Okay. I'm sorry, did someone want to follow up? Yeah.
So here we have north-south magnets, and in the first diagram we showed us we have four types of magnets, with the magnetic field up, the rightwards, downwards, and leftwards.
Oh, you mean I didn't leave you mean the arrows in here?
Yes, and so there are only two types of magnets, and in the first diagram, there were four types of magnets.
Yeah, it's just that this is a simpler version. Okay. This is just giving you the vertical field part, but yes, you always have these magnetic loops. Yeah, thanks. Okay, so yeah, so how do you go from unbunched to bunch? It's going from incoherent to coherent. So this is an example. In life, generally, you think you go from coherent processes, everything becomes incoherent, right? Time, thermal motion removes this. So what are some mechanisms by which you can start from incoherence and get to coherence? So here's a football match going on. Fans come in and they start applauding for their favorite team. Okay? So everybody's clapping, but they're all clapping by themselves. This is like the undulator. Okay? They're all making noise, but it's out of phase. Okay? But some group of people come in together. Maybe 10 or 20 people come together. They sit together, and they start clapping together. So their power is it's an n squared effect, right? The acoustical pressure waves that are going out are 10 times stronger from them than for their neighbors. So pretty soon their neighbors also start clapping coherently with them, and this starts growing, and pretty soon it can sweep. I'm told that at certain football matches where people get really good at this, they can shatter the windows of buildings nearby. And in fact, I was in Hamburg in August when they have a big free electron laser and a synchrotron, and I watched to see in the audience how did this grow. And I could see actually the people just watching hands, you know, and hearing the sound. I could see it growing around the stadium that people were starting to clap together. So it's an example of going from incoherence to coherence. So it's happening in the free electron laser. Somehow or other, the electron beam comes in with all the electrons random, and they wind up in this wave. So the question is, how does that happen? So that's the task for the next slide or two. Here's a wave, the undulator. The undulator has produced radiation the electrons are moving through the undulator, and let's just say there's some wave, it's just started, it's at the beginning, and it looks like this, okay? This is the electric field. So it's just maybe near the beginning of the undulator, okay? And it comes through. And so this is the wavelength. And this is one undulator period here. And the dark line is if there wasn't any electric field produced by the nearby charges, the electron would be on the solid line, come back to the axis here, and go off. But because there is a wave, it's just starting, it's weak, and this is the amplification process just starting. If this electron, as it crosses the axis, is in a region of phase where this electric field is pointing up, then it gets a kick. The electric field gives it a kick up, and now the electron goes on this dashed line, and it comes back to the axis a little bit further along than the original crossing point. If for a different electron that wasn't here but was over here, it gets a kick the other way, and so this weak electric field causes it to come back to the axis too soon. This is starting to produce bunching. Electrons which typically would have all been crossing the axis at this point, now there are some crossing a little later and some a little before, and you have the beginning of a bunch. Okay? It's not so much, but it is always an n squared. So the number of electrons here, although it could be small in the beginning, you're starting to see a little modulation, and you're getting a little bit stronger electric field. So as you go along, this wave is going to increase because of this bunching effect. Okay? So that is the secret of the free electron laser. Why is there bunching happening? Once you get the bunching, you know that you'll add up the electric fields and you'll get this strong effect. But why was it bunching? It's because of this effect. The electric field needs to be included in that calculations of F equals ma and the Lorentz force. This is why we put the electric field in, because we need to include this effect. So maybe I should go backwards here, and yeah. So you're in the beginning, it's just a small effect of this crossing. The electric field is causing a little bit of bunching, but that increases the electric field. So as it moves along further, the electric field is stronger. The bunching, the modulation starts to get stronger, so the electric field. So now you have an exponential growth, okay, which then brings us to a slide. This is a movie by Sven Reike. This was also his PhD thesis in Hamburg at the and it's showing how the electrons start to, So this is as a function of position. And this is in one period, a few periods of the undulator, and the electron beam is now starting to collapse here into these waves. Okay. So what's happening? So here's a diagram. The axis isn't right. This was for not an X-ray laser, so the distance is only a few meters. But as the electron beam is coming into this long undulator, the electrons are just spread out. It's randomly located. I'm not showing all the dots, but there's a uniformity of position. And at a certain point, there's a little modulation starts to occur. A little bit of electric field is strong enough to start this crisscrossing and bunching. And you start to get a little bit of observable bunching, as in the movie. And now the electric fields are becoming stronger. There's there's less randomness and more coherent adding of the fields, and so you start to see a modulation, and eventually it becomes fully modulated and it saturates. Okay? So this would be a great time for a question.
Instead of just increasing...
No, you go ahead. I'm sorry.
Instead of increasing the length of the undulator, can we just do like making them resonant inside the cavity unless they got modulated up to a certain limit?
Yeah, okay, so the question is, rather than make this thing enormously long, could you have a cavity and get amplification that way? And so this is called a free electron laser oscillator. Oscillator is another word for a laser. And there's a lot of work going on about this. The same Kwang Jae Kim, if you were to look up his name and look up FEL oscillator, you'd find, he has a proposal to put crystal mirrors, crystal reflectors at each end and get it going back and forth, and that will give a very narrow bandwidth because of the crystals. So it's a hot topic, but it's into the future a little bit. Yeah, there was a question in the back. Yeah?
I say that one of the hindrances for having an electron laser is to have high current.
Yes.
You don't have at a certain point problem of electron-electron interaction like in Bosch effect?
Well, a good question, yeah. So the question was for the FEL, actually also for the synchrotron. You have a high current, you have a lot of electrons. Why aren't they just kicking each other out of the beam, out of this little bunch? And the issue is, what is their effective mass? Their effective mass is gamma times m. And that's really what keeps them from flying out. So you still lose some. You still have some occasions where the electrons will collide with each other and one will get kicked out. And this is why the synchrotrons have a certain lifetime. After a certain number of hours, they need to replenish, okay, because they've lost electrons. But it depends. So for soft X-ray machines, gamma is lower, the effective mass is lower, the lifetime is measured in hours, whereas in the hard X-ray, it could be a fraction of a day. So yeah. Well, just this is truth in advertising. I've been telling you about one bunch going through the FEL. It turns out that the length of the bunch in the free electron laser is long enough that you can actually have several micro bunches going at the same time. So for instance, at Stanford, but it's quite like this at the other free electron lasers, they'll actually have a few hundred of these little micro bunches going at the same time. They're all at more or less the same wavelength or photon energy, not quite. You know, they're within some band, acceptable band, but they're out of phase with each other for sure. And they're also, so why am I telling you that? Because it's going to affect the spectrum that you see. Each one of these, if they have a different wavelength, slightly different wavelength, it's going to come out in the spectrum. So since the free electron laser, which I've just described to you, started from noise, there is some noise characteristics in the output. And that's what you get to see here. This is what a spectrum, with shot-by-shot spectrum, it's dancing around the spectrum. This is photon energy. It's dancing around because it started from noise. The original wave that I showed you starting at the early, as the electron bunch was entering this very, very long undulator, the kilometer long, when it started, I said there was a little wave there, but that wave started from noise. A bunch of electrons just happened to come together and radiate together. It's like the crowd, the friends who came to the football game and started clapping together. It depended on some cluster dominating locally. And so we have the same thing with this free electron laser. It starts from noise. Some group of electrons happen to get together, and maybe somewhere else in the bunch a different group came together, and that's why we got different micro bunches, a few hundred. So this is what a spectrum would look like. This is data, okay? You'll find this in this chapter on FELs that I told you about. And so there's a spectrum here. So you can do a lot of things here. You have a lot of power. It's in femtosecond duration, maybe 10 femtoseconds or so, a few tens of femtoseconds, but a lot of spectral spikes. So it's okay for some experiments, but in some cases, you'd like to narrow this down. And so what they do is they call it self-seeding. It's basically filtering. For hard X-rays, they'll put a crystal here so that the radiation that's produced, of course the electrons don't want to hit the crystal, so you have to make them go around. So this diagram is not complete. But at any rate, you want to put a transmission X-ray crystal so that only a narrow spectrum goes forward. And then that part gets amplified, and it's a narrower spectrum. Okay? And you get better spectral coherence and better coherence length. So here's an example of what that would look like. Here's a shot. Here's a bunch of shots, different noise, and here's what happens with a single shot with the crystal. So I think I want to stop here and take a question or two. Okay? Yeah, again.
I don't have the number for X-rays. What is the minimum line width you can have for a femtosecond pulse?
Oh, you mean what's the bandwidth limit?
Yeah.
Well, for instance, they're playing, they can get to, with the bandwidths that they get, which is, again, we're in the 1/n bandwidths, or with the crystal, you could get you could set with a crystal here, you could set the bandwidth to be, let's say, 1 part in 3,000 with a crystal monochromator. So that's giving you the bandwidth now. With that bandwidth, what's the shortest pulse you could get by Heisenberg's uncertainty principle? And the answer is a little bit less than a femtosecond, half a femtosecond. So they are pushing into the attosecond regime. Any other, please? Yeah.
So when you saw this coherence beam, so it was already a diffraction pattern right after you pass it through the pinhole. So the one I get at my protein crystal is the same one, or you filter out the...
So in this case, we didn't need to put the pinhole because the electron beam itself was small enough to satisfy the condition. So we never put the pinhole. So actually, the radiation coming out here is narrower than that central radiation cone, actually. It is diffraction limited. You can put some objects here and do the scattering. So for instance, people who do protein crystallography, they need to produce a crystal, a biological crystal, let's say. Okay? And it's a certain size. There's a lot of things they can't make a big crystal out of. They can only make it. And so what they do is they take this small crystal and they put it in front of this coherent beam, and they look at the diffraction pattern, and from that try and analyze what the structure was. So basically, this radiation coming out is spatially coherent. It will produce a very fine diffraction pattern. Okay? It's almost everything you want. You could still improve the phase a bit. In fact, that would bring me maybe a last comment on FELs, and then I'm going to switch to optics. And that is, I told you we started from noise here, just by some random clustering of electrons, okay? At Fermi, the free electron laser in Trieste, the wavelength is longer. It's more like, in photon energies, it goes up to 100 eV or a few hundred eV. It goes up to the so-called water window. But how does it start? It starts with a laser input. So rather than start from noise, they shine a laser into it. They use a Ti-sapphire laser and a frequency double or triple, I forget which way it goes, but they put in a wavelength of a few hundred nanometers. It's a strong, high amplitude wave. And for Fermi, which is producing not hard X-rays, but 100 EV, 50 EV photons, it starts not from noise, but with an impulse, a real seed, a real phase-coherent seed from a true atomic laser, a Ti-sapphire laser. So you can do real seeding, but it doesn't work so well. It doesn't work, really, at harder X-ray wavelengths, just because you can't get a high enough amplitude laser at short enough wavelength. Okay. Okay, so here's some references on free electron lasers. There are two really fine books, so you'll see them in the slides. And there's the chapter I told you about, okay?